Okay, in my last lecture, we saw the following equation describing the total energy E of a simple harmonic oscillator, where the oscillation itself occurs on a flat frictionless surface. The total energy E is 1/2 Ka squared. Okay, in this video, let me show you a couple of basic examples of the use of this expression. We're going to do so with two problems that I've listed together because these two problems are pretty similar to each other. Okay, let's go ahead and copy down the first of these two examples into your notes. So two examples involving the total energy E of an oscillator. Number one, at what displacement of an SHO is the energy half potential and half kinetic? What you have to do in a problem such as this is you have to take what is given there in words and then write it out as a simple mathematical expression. So here's how we're going to do so. Okay, so this is problem number one. Okay, we're taking a look at, right here, a specific point in the oscillation x. It says at what displacement, so then therefore it's looking for a value of x. Okay, and then half of the energy is potential energy, and half of the energy is kinetic energy. Here's how you can write that now as a simple mathematical expression. The potential energy is 1/2 of the total. So it says in the example that the energy is half potential and half kinetic. Therefore, 1/2 of the total energy is equal to the potential energy. And now let me just go ahead and write the potential energy as 1/2 kx squared. And then we have here on the right-hand side of the expression, 1/2 times the total energy, which is 1/2 Ka squared. And then what we do is we solve for x. When we do solve for x, we end up with a fraction of a. So in other words, it's at some fraction of the amplitude of the motion as the oscillation occurs. So with examples like this and the one that follows, as you'll see, usually a bunch of stuff cancels out. So let's go ahead and cancel out the 1/2s here and here like so. Let's cancel out the k here and here. And then here's what's left over. I have x squared and then 1/2 times a squared. Let's go ahead and take the square root of both sides, and I'll just write down the magnitude of this displacement x. So then therefore the magnitude of the displacement x is 1/√2 times a. So the answer is not 1/2 of a, as you may have guessed as we initially wrote down the problem. Instead, the answer is 1/√2 times a. So at this position on either side of the equilibrium position, this then means that the energy is half kinetic and it's half potential. Okay, let's take a look at number two, which is a similar sort of setup. Okay, let me do that here in the lower board. Okay, so once again, what we have to do is we have to take what is given there in words and write it out as a mathematical expression. So what fraction of the total energy is potential if the displacement equals 1/2 the amplitude? So in this problem, we are given the value of x. So once again, here's a simple drawing. Here's the equilibrium position, and now we're specifically given that x is equal to 1/2 the amplitude. And then here's how you take what is given there in words and write it out as a mathematical expression. So what fraction of the total energy E is the potential energy if x is equal to 1/2 a? And now what I do is I write the numerator of the expression as 1/2 kx squared, write the denominator as 1/2 Ka squared. Okay, I'm going to go ahead and immediately cancel out the 1/2 k's, that is here and here. And now let's go ahead and write the x in the numerator as 1/2 a. So I'm going to have here 1/2 a quantity squared over a squared in the denominator like so. And if you do the math in the numerator of the expression, all of the a's will cancel out, and then you end up with 1/4, which is equal to 25%. In other words, specifically at this point in the oscillation, 25% of the energy is potential energy, and then therefore 75% of the energy is kinetic energy. So that's how you approach these simple problems involving total energy. You basically write it out as a mathematical expression and then solve for whatever it is that we're looking for. Okay?